Hi everybody, thank you for attending my presentation. I'm Yuhong from Huazhong University of Science and Technology. The paper I'll be presenting today is titled Anti-Resolution with Hierarchical Graph Attention Networks. Okay, let's begin to introduce the paper. Anti-resolution, abbreviated ER, aims to find whether two data entities refer to the same entity. Figures show two pairs of products from two online shops, and ER aims to determine whether each pair of product entries are the same product entity. Nevertheless, ER remains a non-trivial task because natural language texts often have this application difficulty due to the quantity of context information and topically coherence. For example, consider the two pairs in the figure. Existing ER methods would give incorrect results. The first pair of entries share many common words, and thus would be considered as a matching. However, they refer to two different software. For the second pair of entries, which are a match, would be labeled as unmatched, since what Adobe Spark are important and what's in the description attribute are not. A key challenge for successfully ER is figuring out how to capture semantic and latent context. However, these recent ER models still have two weaknesses. First, they typically assume that all words and attributes are equally important for an entity, which often fails to identify the discriminative words. Second, anti-discriminations often include ambiguous phrases. A word in different domains may be polysemous or have different meanings. The formal definition of the ER problem is now given. To solve this problem, a straightforward way is to take a query entity from D and then compare it with other candidate entities in D dot. Most of the existing methods treat those pairs independently, which is referred as the pairwise ER. We also consider collective ER, in which a query entity has many connective entities, as the entities contained in the same document are often semantically related. Collective ER models jointly determine matching for related pairs. However, ER problems still have three challenges. First, pairwise ER models ignore the semantic relation between entities. Second, collective ER model doesn't work among heterogeneous data sources. Third, there is no single uniform solution to both of these problems. Next, let's introduce our framework Hierarchical. Hierarchical combines the self-attention and graph-attention mechanism to solve ER problems for the first time. First, Hierarchical uses a transformer, which generates highly contextualized embeddings and can identify the discrimination words based on the self-attention mechanism. Second, Hierarchical further uses a hierarchical graph attention network model to identify important features for learning better embeddings, thus optimizing the matching performance. Based on the pairwise ER model, we further propose a collective ER model, Hierarchical+, which jointly determines multiple candidate pairs where there is a matching. Hierarchical+ is able to explore the relationship among entities for better accuracy. Especially, we propose a new type of graph called hierarchical heterogeneous graph, shortly HHG, to represent entities, attributes, and tokens. HHG proposes three types of nodes, and each type forms a layer. The node relation composes three types. First, token attributes relation, describing that attributes that are composed of the tokens. Second, attribute entity relation, describing that entities are composed of the attributes. Third, entity-entity relation, describing the relation between entities. There are two advantages of the proposed HHG. First, HHG preserves the hierarchical structure of an entity, and we can read the entity embedding from bottom to top by following hierarchically in the HHG. Second, corresponding to a query entity, multiple candidate entities can be represented in one graph. The representation is particularly useful for the collective ER decisions. We propose to learn contextual embeddings to enrich the original word embeddings. We first present the challenges of using word embedding technique for solving the ER problem. First, the embedding of some brand-specific words are not learned, but they are very discriminating in the ER problem. Second, The same word in different attributes or different entities may have different contextual information. To address the problems, we argue that it would be important to use a contextual information by considering three levels of context. The token level context captures semantic meanings in the sentence. The attribute level context captures attribute semantic, and the entity level context with common word redundant information. And we propose to use a attention mechanism to derive distinguishable contextual information for the same word in different contexts. Next, entity aggregation. This component hierarchical aggregates word embeddings to derive entity embeddings based on HHG. As shown in the left part of figure, the hierarchical aggregation includes two steps: attribute summarization and entity summarization. Entity comparison. This component hierarchical compares the entity similarity in attribute level and entity level to derive entity similarity and embeddings. Inspire the idea of multi-view learning. We can see the different attributes as different views of an entity. Furthermore, to handle the collective ER, we link the query entity and its candidate entities in a matching relation network. Based on this relation network, we apply the entity alignment, which enables us to find discriminative tokens among the candidate entities collectively. Next, I will introduce our experiments of our HierarchiCal models. First, we use 9 public datasets from Magellan. In addition, we use WDC product matching data, which are categorized into 4 different domains. And the 4 datasets are combined into one dataset to generalize a multi-domain dataset. Table summarizes the Magellan and WDC datasets. We compare the HierarchiCal with 3 baseline models. Magellan is a widely used anti-resolution tool based on traditional machine learning. DeepMetric is a state-of-the-art RNN-based model. We also compare with Ditto, and it's based on transformer. Finally, for the pairwise work, we use S1 SOC as a common evaluation metric. Figure shows the effect of attention mechanism on matching. As we can see, here GAT gives more importance to discriminating words and important attributes. The here GAT achieves the best performance on most datasets and improves the F1 SOC by up to 8.7% of the best baseline. And here GAT achieves best probabilities on 30 datasets. Finally, here GAT achieves stable results on WDC datasets. Here GAT requires only one-half of the training sample to obtain similar results as Ditto. Comparing with DeepMetric, here GAT only requires 1/8 of the training samples to achieve similar performance. The datasets for pairwise ER cannot be used to evaluate collective ER models. We apply a new blocking method on classical Magellan dataset and the latest DI2KG dataset to generate benchmark datasets. Table summarizes the total number of candidates for all the query entities. In addition to the baseline models used in the pairwise ER, we also consider additional models optimized for collective ER. We use Hierarchical to optimize DeepMetric for the collective ER, and we use several graph neural network models. The evaluation results on 5 Magellan datasets and DI2KG datasets are present in table. The results show that it's effective to maintain the relationship within candidate set. Here GAT Plus improves the F1 SOC of Here GAT by an average of 4.3% on the Magellan datasets. Finally, we evaluate the efficiency of models. Figures show that the training time of Here GAT increases linearly. Compared to Here GAT, Here GAT Plus takes 3.5% more training time, mainly due to the entity alignment operation and removing redundant information. To evaluate the generality of our proposed method over different transformer-based pre-trained language models, we compare with Ditto with respect to language models in 3 different model sizes: Distill-Bot, Robot, and Robot Large, and results are summarized in the table. It shows that Here GAT outperforms Ditto for all language models, and also shows that Here GAT Plus better performs Here GAT for all language models. We evaluate the effectiveness of the proposed method for modeling context. We compare the following variants. First, non-entity without entity level context. Second, non-attribute without attribute level context. Third, non-text without any context, i.e. word embedding only. The results show that all three types of the context attribute to the results of HGAT+. The semantic information in the word embedding fits the context, making the final embedding more discriminating for ER problem. By comparing weight averaging method and two other methods, this experiment is to evaluate the effectiveness of our proposed attribute summarization method in multi-view learning. Weight averaging based on scheduled attention achieves the best accuracy because it enables us to highlight more discriminating attributes, make it easier for the classifier to determine matching relation. We evaluate the effectiveness of the entity comparison components when compare the following variants. First, HGAT plus, the complete model. Second, non-sum, HGAT plus without entity summarization component. Third, non-alignment, HGAT plus without entity alignment component. These results are presented in table. The table shows the effectiveness of these components in HGAT plus. Now, I will give the conclusion of our paper. First, we first define the hierarchical heterogeneous graph HHG to describe entities as well as their attributes and words. Second, we propose a normal solution called HGAT. To the best of our knowledge, this is the first work to combine the self-tension and graph tension mechanism to solve ER problem. And we further propose to learn contextual embedding to enrich the word embedding for better performance. Third, we propose a HHG-based collective ER model, HGAT+, in which a query entity and candidates are represented in one graph for ER decision. Finally, by comparing with several ER baselines, including the state-of-the-art model, deep measure, and detail on several databases of different size and domains, we provide an extensive empirical evaluation on HGAT and HGAT+.